Imagine, one morning a tiny coin-sized dark sphere appears on the ground. It looks harmless, the size of a quarter, maybe a nickel. What happens next? Would it swallow the city, the planet, or simply vanish in a puff of quantum fuzz? Today we'll follow the physics step by step and separate myth from real risk. This is a careful, evidence-first thought experiment. What the equations of general relativity and quantum theory predict, what the observational constraints say, and what practical consequences would follow. First, we must be precise about what coin-sized means. If we mean an event horizon, the black hole's actual gravitational surface, with a radius comparable to a coin, the mass required is enormous. The Schwarzschild radius r_s is related to mass m by r_s equals sine 2gm c squared. Rearranged, the mass needed for a given radius r is m equals sine rc squared, 2g. Plugging in r equals sine 1 centimeter, about half a typical coin's diameter, gives a mass of about 6.7 x 10 circumflex 24 kilograms, roughly 1 Earth mass. Calculation note, r equals sine 0.01 m/m6, 73 x 10 to 24 kg, that is 13 Earth masses. The Schwarzschild relation and this conversion are standard in relativity textbooks and references. That result is the first crucial counterintuitive point. A black hole whose event horizon is the size of a coin would contain roughly the mass of the entire Earth. If such an object suddenly existed sitting on the ground, its gravitational field at distances much larger than a few centimeters would look almost identical to Earth's current gravity, only if the mass distribution around was unchanged. But you can't fit the Earth's mass into a tiny coin without dramatic consequences. In practice, you'd have a mass concentration change that would severely perturb everything nearby. To truly understand the physics, we need to be precise. So let's consider two alternative thought experiments, because the seemingly simple phrase coin-sized black hole can be interpreted in two radically different ways, each with its own astonishing outcome. First, let's imagine the event horizon itself is the size of a coin with a radius of a few centimeters. The physics of black holes dictates that the size of an event horizon is directly proportional to its mass. For a radius this small, the math reveals a staggering implication. The black hole would have a mass roughly equivalent to that of our entire planet, Earth. If such an object appeared on Earth's surface, it would be a near-Earth mass object concentrated into a single point. The local gravity would be unimaginable. The atmosphere would be instantly siphoned away while the ground beneath it would be pulled in, generating catastrophic seismic waves. Immense tidal stresses would stretch and tear the planet apart, triggering global earthquakes as the crust collapses. Even the moon would be thrown from its orbit. In short, the sudden appearance of an Earth mass, coin-sized black hole on the surface is a planet-ending event. But what about the second interpretation? This is where people imagine an object that simply has the mass of a coin, say a few grams. If you could compress that small mass enough to form a black hole, its event horizon would be infinitesimally small, trillions of times smaller than a single proton. At this scale, classical gravity gives way to the bizarre world of quantum mechanics, where a phenomenon known as Hawking radiation becomes dominant. Stephen Hawking's groundbreaking theory predicts that black holes aren't entirely black, they leak energy. For very tiny black holes, this leakage becomes a powerful torrent. It would radiate away its entire mass as a burst of high-energy particles in a tiny fraction of a second. This evaporation would be explosive, releasing a significant amount of energy, but it would be over almost instantly. It wouldn't have time to grow or swallow anything substantial. This is precisely why physicists aren't worried about creating micro-black holes in particle accelerators. They pose no realistic threat. So which scenario is physically plausible on Earth? Creating an Earth-mass black hole from nothing violates the fundamental law of conservation of mass energy. According to Einstein's E=mc2, mass and energy are two sides of the same coin. To manifest a black hole, you'd need to supply an equivalent amount of energy, which for an Earth-mass object is a staggering figure. This isn't something that can appear spontaneously. It would require converting our entire planet into a single point, or somehow delivering an energy payload equivalent to the sun's output over millions of years. On the other hand, microscopic black holes are a different story. They have been hypothesized in some speculative theories like those involving extraspatial dimensions where gravity might become much stronger at tiny distances. However, even if they could be created, physics predicts they would be incredibly unstable. Due to a process called Hawking radiation, they would evaporate in a near instantaneous flash of particles, posing no threat of runaway growth. So far, collider searches and astrophysical observations have found no evidence for them, placing strict limits on their production. The LHC safety studies and subsequent experimental searches found no sign of dangerous micro-black holes, and cosmic ray arguments show nature has already performed far more energetic collisions than human colliders without catastrophic outcomes. Let's assume the scariest reading, an event horizon of coin size with Earth-scale mass, and track the immediate physics. A concentrated mass comparable to Earth would change the gravitational potential dramatically near the point of appearance. If the mass truly moved from being distributed through the planet into a tiny volume, enormous mechanical stresses would be produced. The crust would collapse inward, massive earthquakes would ripple worldwide, and large portions of mass near the site would be pulled in quickly. Objects within a few kilometers, buildings, oceans, the crust, would experience catastrophic infall. On longer timescales, the entire planet would face destruction. The immense gravity gradient would create powerful tidal forces, stretching and tearing the Earth apart. This shredded planetary matter wouldn't just fall in. It would form a superheated accretion disk, a swirling vortex of plasma glowing brighter than the sun as it spirals into the black hole. This process would effectively erase our world, leaving behind only a solitary Earth mass singularity. That's the end of the planet as we know it. What about accretion, the black hole eating the rest of Earth? If a compact Earth mass black hole sits embedded in the planet, matter falling in will release gravitational energy, heat and radiation. But the timescale for swallowing the entire Earth depends on accretion physics. For very large black holes, classical accretion may be limited by angular momentum and by the rate at which matter can be delivered to the horizon. However, if the mass is suddenly concentrated, the immediate dynamics are violent and fast in the vicinity. Tidal forces near the horizon are enormous and will shred nearby material, leading to rapid infall of a lot of mass. In short, catastrophic and fast on geological timescales. This differs from slowly feeding a tiny primordial black hole placed quietly in the planet's core. The details matter. Contrast that with the tiny mass micro-black hole scenario, a microscopic black hole with, for example, mass on the order of 10 circumflex 11. 10 circumflex 12 kg would still be extremely small and, depending on theory, might evaporate due to Hawking radiation or be too tiny to accrete significantly. Most standard analyses show that any black hole small enough to be harmless to Earth would either evaporate quickly or be so feeble that it would take far longer than the age of the universe to accrete significant mass. That's why mainstream safety assessments for high-energy experiments conclude no risk of Earth-devouring black holes. Let's consider another angle: observational constraints. If dangerous micro-black holes could form spontaneously, we should see evidence of them elsewhere in the universe. Astronomers actively search for primordial black holes. Hypothetical black holes formed not from stars but in the dense, chaotic environment of the very early universe. If these were common, they would leave undeniable astrophysical signatures. We'd see frequent microlensing events as they pass in front of distant stars, or detect bursts of gamma rays from their evaporation. Yet, extensive surveys have found no such evidence, placing extremely tight limits on their abundance. That powerful empirical constraint supports the conclusion that Earth is not at realistic risk of spontaneous dangerous black hole creation. But what about Hawking radiation? Couldn't a small black hole evaporate in a devastating explosion? This quantum effect, where virtual particle pairs are separated by the event horizon, causes black holes to lose mass. The rate scales inversely with mass. Smaller black holes are hotter and radiate faster, while larger ones are colder. A black hole with the mass of our Earth would be astronomically cold, with a temperature far below that of the cosmic microwave background. It would absorb more energy from its surroundings than it radiates away. In this scenario, Hawking radiation would be utterly negligible and certainly wouldn't save us. Conversely, a black hole small enough to evaporate violently must have a tiny mass to begin with. Such an object would be so microscopically small, with such a tiny gravitational cross-section, that it would have virtually no time or opportunity to consume matter from the planet before it evaporated harmlessly. The bottom line is this: physics presents two distinct scenarios. Either you have a microscopic black hole that evaporates harmlessly, or a macroscopic massive one whose appearance is catastrophic. There's no comfortable mid-ground where a coin-sized event horizon appears and slowly swallows the world. Its accretion rate would simply be far too low. Finally, what are the real-world takeaways? First, the math is unforgiving. An event horizon size is directly proportional to its mass. Second, robust experimental and astrophysical limits, including safety reports from the LHC, strongly disfavor their spontaneous creation. Third, our intuition fails us. We often conflate visually intuitive size with mass and energy, and that confusion causes needless fear. If you want to explore this more deeply, read the technical safety reviews from collider programs in the literature on primordial black holes and Hawking evaporation. The science is rich, technical, and fascinating. If you enjoyed this careful physics-based exploration of extreme what-ifs, subscribe. We'll keep unpacking real science behind dramatic hypotheticals and show how equations, experiments, and observations together separate real danger from sensational speculation. Thanks for watching.